Let us now discuss a 3-rotor system. This horizontal line or this section represents a shaft on which 3 rotors are mounted. Now the rotor can be, for example, assume this to be the rotating part of an engine. Now the rotating part of an engine directly connects with a flywheel. So let B be a flywheel. Now this is a rotating, A be the rotating part of an engine. Now let the shaft from the engine be connected to the flywheel. So let C be the flywheel, and the shaft when extended, let it be connected to another rotating disc, which let us assume to be a propeller. So I just told you about an example where 3 rotating system comes on a single shaft. So such a system can be taken into account as a 3-rotor system. So let A, B and C be the 3 rotors placed on a single shaft. Now how will we analyze the torsional vibrations occurring in this shaft in such a system? Here also, as in the previous video for the 2-rotor system, the questions may be asked to find out the node of vibrations that are occurring in this system. Secondly, you will be asked to find out the different amplitude of vibrations of these rotors, and you may be asked to find out the natural frequency of vibration of the rotors. So before getting into the technical or equations part, you have to understand how we are going to find out the node shapes or the nodal points. See, certain assumptions or certain basic fundamentals that you have to understand here is, as you have 3 rotors, always you have a scenario that 2 rotors will be rotating in same direction. Always 2 rotors will be always rotating in same direction, and the remaining 1 rotor will be rotating in the opposite direction. Always the cases will be like this. That means either, suppose we can assume A and B to be rotating in the same direction, and let C be rotating in the opposite direction, or else let A and C be rotating in the same direction, B in the opposite, and let C and B be rotating in same direction, A in the opposite. But whatever may be the condition, these 2 things will be always satisfied. That means 2 rotors will be always rotating in the same direction, while 1 rotor will be rotating in the opposite direction. Now let us analyze all these scenarios within this 3-rotor system. Now let for the first case, let A and B be rotating in the same direction, and let C be rotating in the opposite direction. See, one thing we should remember is, if this is a shaft and you have a rotor here and a rotor here, nodes are formed between the shaft only when both the rotors are rotating in opposite direction. If both rotors are rotating in same direction, there will be no node of vibration, no vibrating nodes will be generated. That means no point will have 0 amplitude of vibration. So first case, A and B same direction, C opposite direction. Then how will be the nodes occurring? Okay. The node of vibration will be C. As this is the scenario, A and C will be rotating in opposite direction. That means definitely in between A and C there should be presence of 1 node. So that node, let it be like this. Amplitude of vibration here, it reaches to a certain point, maximum value, then it decreases, and at a certain point the amplitude decreases to 0. Then it extends to the corresponding amplitudes for the C rotor. Now as C and B are rotating in opposite direction, see, A and C opposite, C and B opposite, again there will be generation of a single node point between C and B. So that can be connected and drawn like this. So these 2 are the nodal points generated here. So now we have to understand certain terminologies or certain alphabets that we are placing in this figure. Distance between A and C, let it be, first portion of the shaft, let it be L1, and the second portion of the shaft, let it be L2. Next, distance from rotor A to the immediate node that it is making, let that distance be equal to LA. See, understanding these terms are very important. What is LA? LA is the distance from rotor A to the immediate node that rotor A creates. LA. Similarly, let this distance be LB. So what is LB? LB is distance from rotor B to the very immediate node that rotor B generates, that is LB. And now with respect to rotor C, you have two sections. Now with C, let this distance be LC1. What is LC1? The distance from rotor C to the node generated between C and A, that is LC1. See, the distance from rotor C to the point of node between C and A. So this distance will be what? This will be LC2. What is LC2? The distance from rotor C to the node between C and B. So please remember all these notations. Whatever be the kind of sense of rotation these rotors are changing about, these notations will remain same. That means sense of these notations. That means what is LA? LA will be always the distance made from rotor A to the very immediate node that it makes, that is LA. LB, the distance from rotor B to the very immediate immediate node that B itself generates. What is LC1? Distance from rotor C to the node made between A and C. LC2, distance from rotor C to the node made between C and B. Now let us get into the second case. Let C and B rotate in same direction and A rotate in opposite direction. C and B rotating in same direction, A is rotating in opposite direction. Now let us check out how the node shapes will change. As A and C are rotating, in the opposite direction, or as B and C are rotating in the same direction, there won't be any node generated between C and B, because B is rotating in one direction, C is rotating in the same direction. That means shaft will also rotate in the same direction. There is generation of zero node between them. So there the amplitudes may change in this manner. A straight line. There is no node generation between C and B. Next, A is rotating in the opposite direction. That means C and A will rotate in the opposite direction. Hence, there will be a single node generated between A and C. So, hence, let that node be represented like this. Let that particular node be represented like this. So, here no node between B and C, and between C and A there will be representation of generation of one single node. Now let us represent L1, L2, LA, LB, etc. L1 will be remaining the same. This distance will be always L1, and this distance will be again L2. Now, as there is a node between A and C, from rotor A, the immediate node generator is here. So this distance will be becoming LA. Now from C, you have a node between C and A. That means this distance will be LC1. Same to the previous case. Now, as there is zero node between B and C, we can't take the distance LB in between C and B. So what we are going to do is, we are going to imagine that if this curve of the amplitude continues its generation, let this come and meet somewhere at this point. If we extend this one straight away, this is a straight extension, let it come and meet at this point. Hence, this node can be considered as the node that is generated by B. Hence, let us mark this distance equal to LB. What was LB actually? Distance from rotor B to the node that it generates. As in this case there is no node between B and C, let us extend this amplitude. Imagine that this amplitude is being extended, it is being going over the rotor C and it meets this shaft at this point. So let this distance be from B to the node that B has been generating. So let this distance be LB. Now then what will be LC2? What will be LC2? The distance of C, distance from rotor C to the node between B and C. As there is no node between B and C here, we have to again go for this imaginary nodal point. So this distance we have to keep it as LC2. This distance will be LC2. Pause the video, look at the figure carefully, note down the figure yourselves and try to understand how these distances LC1, LC2, LB and A has come here. The sense of this distance is the same as the first case that we discussed in the 3-rotor system. Now let us come to the third case. Let A and C rotate in same direction and let rotor B rotate in opposite direction. So as A and C are rotating in same direction, there won't be any node of vibration between A and C. Hence let the curve be passing like this. Now as C and B are having opposite direction, C and A are having same direction but B is in the opposite direction, hence C and B will be in opposite direction. There will be generation of a single node. So let us represent that particular node here. Now similar to the previous cases, let us try to understand how the distances are coming. Now as there is no node between A and C, let us extend this one. Let us imagine it is meeting here at some single point here. Okay. Hence the distance LA will be distance from this rotor position A to this generated imaginary node from A. This will be LA. This distance will be always L1 and this distance will be always L2. Now here as we have no node between A and C, let us extend this amplitude curve to some further distance and let this imaginary point be the node created by rotor A. So this distance will be LA. And hence what will be LC2? LC2 will be this distance. It is the distance from rotor C to the imaginary node. Here as there is no real node, the imaginary node between C and A, that is this one. So let it be LC1. This distance can be marked as what? LB, because distance from rotor B to the immediate node that B is creating, and the distance from rotor C to the node between C and B will be nothing but LC2. Now as in the case of the 2-rotor system, you will be asked to find out the natural frequency of vibration, the location of the nodes generated between the rotors as well as the amplitudes of vibration. Now as all the 3 rotors are being connected to a single shaft, let us equate all the frequencies, natural frequencies. Now these natural frequencies Fna equal to Fnb equal to Fnc. Now let us write down as we have the middle rotor as C, Fnc equal to Fnb. Whatever be the order of writing, there is no issue in that. So now this can be written as 1 by 2 pi into Qa by Ia. So equal to 1 by 2 pi into Qc by Ic, and this is equal to 1 by 2 pi into Qb by Ib. Now we know that Q is equal to G into J by L, where G modulus of rigidity, J is the polar moment of inertia and L is the length of the shaft. So this 1 by 2 pi will get cancelled, square roots can be cancelled out. Remaining will be Qa by Ia equal to Qc by Ic equal to Qb by Ib. Substituting this value here, as we have done several times before, we can rewrite this one as Gj divided by IaLa equal to Gj divided by ICLC equal to GJ divided by IBLB, because G and J will be always a constant. Now, from this equation we can cancel out GJ and GJ from all the terms. So remaining will be 1 by IALA equal to 1 by ICLC equal to 1 by IBLB. Now in the case of distance LC, you have two portions, LC1 and LC2. So this can be rewritten slightly in one format as 1 by, this distance can be written as LC1 plus LC2 multiplied by, this can be written as 1 by, as this has two portions, LC1 plus 1 by LC2 multiplied by 1 by IC equal to 1 by IB into LB, and this portion also 1 by IA into LA. Again we can slightly change this one. IC1 can be written in terms as 1 by IALA equal to 1 by IC1. How can we write LC1? As this distance is L1 and this distance is L2. For this scenario I can change now up to this one, up to this condition. This is the generalized equation that we get when we equate all the natural frequencies. Now after this one, the LC1 and LC2 equations can be modified in certain manner. Those can be according to the node shapes that you obtain. See, we obtain this condition. This is a two node condition. This two node condition is occurring only when A and B are rotating in same direction and C rotating in opposite direction. But if A and C were rotating in same direction and B was in opposite direction, you will obtain only a single node condition, because here there won't be any node, only here you will represent it, you will get a node. Similarly, if B and C are rotating in same direction and A in the opposite direction, there will be again the case of single node. You will obtain a node between A and C only, there won't be any node between C and B. So now according to these three scenarios, you can slightly change the values of LC1 and LC2 according to the marking of the lengths. See, in this case, for an example, in this case, I can write LC1 equal to L1 minus LA. Similarly, I can write LC2 is equal to L2 minus LB multiplied by 1 by IC equal to 1 by IB and LB. Now, in the question, you will be definitely provided with moment of inertia of A, B and C, and other certain data will also be given. Now, either you can equate these two equations, or you can equate these two equations. 1 by IALA equal to 1 by IBLB. That will give you IALA equal to IBLB. Now, either you can write the total equation in terms of LA or in terms of LB, then take that particular value, then equate these two and put the value of LA is equal to in terms of LB or LB in terms of LA. So, using this scenario, you can solve for LA and LB. Now, see, this is the generalized equation. How did we manipulate this equation? Only for the case of two node condition. If this was the case of single node condition, I have to rewrite this equation again. So according to the cases, you have to slightly change or vary the type in which you write LC1 and LC2. Now this was the case for finding out LA and LB. Now for finding the natural frequency, you can find out natural frequency of vibration of any one of this rotor, because all the three natural frequencies are equated to same value. That means F and A is equal to what? 1 by 2 pi into square root of, it is QA by IA. That can be written as G into J divided by IA into LA. You will be provided with all the values. LA you will be finding out from this one. You can directly get the value of natural frequency in hertz. Then, if you are asked to find out the value of amplitudes, for that we can write the equation. in this case you can write it as amplitude of A divided by amplitude of C can be written as length A divided by LC1. This is one method of writing. This is one equation. Okay. Now the second equation can be written as amplitude of B divided by amplitude of C is equal to LB by LC2. This is the second equation for amplitude. These are the equations for finding out amplitudes. Now in this one, if no amplitude is given, you can again assume any one amplitude. That means amplitude of A can be assumed to be 1 radians. Then you can substitute 1 here. You have already found out LA, LC1 and all, you will get AC. Now finding out AC and substituting the value of AC here, you have LB and LC2 from these equations, you can get AB. So in this manner, whatever the required questions may be asked, required values may be asked, you can substitute, resubstitute and rewrite the equations and find out all the values. Generally, once again I am going to tell you, the asked required values will be always LA and LB or LC1 and LC2 according to the finding the location of node shapes. Then you will be asked to find out natural frequency of vibration. Then you will be asked to find out amplitude of vibration. So go through this video once again. Be thorough with the fundamentals. Thank you.